A package can pass an electrical model, remain below a thermal limit, and follow a feasible assembly route, yet still be unready for volume production. In 5D, 3D, chiplet, and DCP programs, signal behavior, power delivery, heat flow, materials, assembly variation, test access, and yield interact. Readiness must therefore be treated as a system claim supported by correlated evidence. The first validation track is signal integrity. Verification begins with interfaces, channel lengths, interconnect transitions, return paths, reference planes, discontinuities, package escape, coupling, and package-to-board interaction. The evidence must identify model versions, dielectric and conductor assumptions, temperature range, termination conditions, aggressor cases, power conditions, and pass criteria. It must also distinguish confirmed supplier data from package design inputs and unresolved assumptions. Power integrity belongs in the same review. Transient current, voltage noise, package inductance, decoupling, die activity, and board interaction can change high-speed interface behavior. A narrow eye diagram assessment is not enough. Before simulation is signed off, the team should define how critical conclusions will be measured, including test structures, accessible nodes, representative workloads, environmental conditions, instrumentation limits, and acceptance criteria. Planning correlation after prototypes exist may leave essential behavior unobservable. The second track is thermal performance. A credible thermal model starts with realistic power maps rather than a single total power value. Logic, memory, interfaces, and power management functions may produce hot spots at different times. Heat sources, materials, interfaces, board paths, ambient conditions, airflow, heat spreader assumptions, and the intended cooling system all need definition. Measurements should reproduce the workloads, reference locations, ambient extremes, and cooling states used by the model. Any mismatch must update the assumption set and margin assessment. Thermal review must also connect cycling, gradients, mechanical stress, interface degradation, and material expansion behavior to relevant reliability risks. Compact integration may shorten electrical paths, but it can also concentrate heat and increase system exposure. The third track is manufacturability, whether the production intent design can be assembled, inspected, tested, and traced repeatedly within a controlled process window. Reviews should cover die handling, substrate or interposer condition, alignment, bonding, interconnect formation, applicable underfill or thermal materials, inspection, test insertion, traceability, pack-out, and non-conforming unit disposition. Design for manufacturability work must occur early enough to change architecture, routing, tolerances, materials, inspection features, and test access. Pilot builds then challenge engineering assumptions with actual materials, equipment behavior, inspection results, test coverage, and early yield. The executed process must be compared with the planned process. Deviations, rework, escapes, recurring defects, and unexplained variation require documented causes, containment actions, owners, closure evidence, and affected revisions. For release gates, connect these tracks. Gate 1 defines package and system constraints, including interfaces, performance targets, power maps, cooling, test goals, reliability needs, intended volume, open decisions, and evidence ownership. Gate 2 reviews electrical, thermal, mechanical, materials, and manufacturing evidence together. It tests whether an improvement in electrical density, for example, creates problems in heat removal, assembly, or test access. Gate 3 correlates prototype measurements and pilot observations with modeled behavior. Important deviations need explanations and closure plans before broader production commitment. Gate 4 authorizes controlled volume release only when the technical baseline, process controls, acceptance criteria, traceability, reliability evidence, change notification, escalation rules, and residual risks are documented. High-risk gaps, such as uncorrelated critical assumptions, narrow thermal margin, unexplained pilot yield, or missing traceability, should block release. Bounded uncertainties may proceed only with assigned ownership and targeted controls. Volume readiness is established when models, measurements, factory evidence, and production controls tell one traceable, consistent story.